Okay, so let's move to the next question, which is we have three metal plates having same area A and are placed as shown. Okay, you can see the diagram. The middle plate is given a charge capital Q. Find its potential. Okay, so the other two plates are grounded, and the middle plate you have to find its potential. So Shrikant will tell us how to approach this question.
So we can quickly say that potential of this plate and potential of this plate are both equal and are equal to the ground, and so we can equate it to 0 for both of them.
Okay.
Now we will draw Gaussian surfaces like this.
Gaussian surface.
Gaussian surface.
Okay, yes.
And we'll find out that E dot ds will be equal to 0 because here the electric field is in this direction.
Yes.
So at these surfaces E dot ds, since it is
Okay, electric field is parallel to the surface.
Yes. So it is 0.
Okay.
And in these surfaces you will see that there is no electric field as such. That says E dot ds is equal to 0.
Okay.
From this we can conclude that summation of Q enclosed is equal to 0.
Yes.
So from that we will say that, say suppose a charge Q is on this face, then a charge minus Q is on this face.
Yes.
So if there is a charge Q on this face, then there is a charge capital Q minus small q on this face.
Yes.
And a charge small q minus capital Q on this face.
Okay, using the similar concept, like if we take the Gaussian surface on that side.
Exactly.
Okay.
So the electric field at a point in this space would be equal to, do you remember the electric field due to a sheet of having charge density sigma?
Sigma by epsilon naught.
Exactly. Sigma by epsilon naught.
Okay.
So since it is influenced by this side as well as this side, it will be equal to 2 sigma by epsilon naught.
Okay.
And it won't be affected by this charge and this charge
because they sum up to 0.
Because they are equal and opposite.
Yes.
So this is the electric field. So the potential difference between this surface and this surface would be delta V is equal to minus of dot dr, which is equal to minus 2 sigma epsilon naught into 3d.
Yes.
Similarly,
yes.
So now this means that it is equal to minus 6 sigma d by epsilon naught, which means the plate having charge Q is 6 sigma d by epsilon naught higher at a higher voltage of this value.
Okay.
Now we'll what is sigma exactly? Sigma in this case is equal to Q by A.
Yes.
So we'll use the same concept and we'll write delta V for while traveling from plate Q to the other plate.
Yes.
So this would be delta V is equal to same minus E bar dot dr, that would be 2 sigma by epsilon naught, let us call it sigma 1.
Yes.
Into d minus.
Okay.
And this is equal to 2 sigma 1 d by epsilon naught, where sigma 1 is equal to capital Q minus small q by area.
Can you show it in the diagram? Okay, Q, capital Q minus small q. Okay. Shouldn't be the minus sign.
Yeah, there is a minus sign.
Okay, minus sign.
There is a minus sign.
Yes.
This makes it minus. So adding up both the potentials should give us 0. That is delta V from the first grounded plate to the next grounded plate.
Okay, I mean going from the left side grounded plate to right side grounded plate, total change in potential we are calculating.
Exactly.
Okay.
So, which means 0 is equal to minus 6q d by epsilon naught minus 2 capital Q minus small q d by epsilon naught.
Okay.
So from this we get, we're cancelling terms.
Yes.
So what we'll get is 2q is equal to 4 minus 4 small q.
Okay.
So small q is equal to minus q by 2.
Okay.
So since small q is equal to minus 2 by 2 minus q by 2, v is equal to, using this,
Yes.
v is equal to minus 6 sigma, that is minus q by 2 d by epsilon naught.
You also have to divide it by a, because sigma is equal to q by a.
Exactly, divided by a.
Yes.
So which is equal to 3qd by epsilon naught a.
Yes.
Is equal to v. This is our answer.
Okay. Because
So-
the potential of the left grounded phase is 0, so delta V gives us the absolute value of the potential at the of the plate of having charge capital Q.
Exactly. So what we used here is the conservative nature of electric field,
Okay.
which because of which delta V between 2 points is constant,
Okay.
irrespective of the paths taken.
Okay. Yes.
And we calculated this and then added the potential differences to find the final potential and equated it to 0.
Okay. Yeah. So that was the overview of this question. Okay, so here we are given a question. The question is, a dielectric slab of width T is placed between a parallel plate capacitor. Okay, find the effective capacitance of the system, and the capacitor plates are square plates of dimension A into A. Okay, so dimension of the square plate of capacitor is A into A, and the T width dielectric is inserted between them, and the dielectric constant, let us assume that it is given to be K, capital K. The dielectric constant is given to be capital K, let us assume that, and we will find the answer in form of K. So
So notice that this slab is kept in a slant way at an angle theta. So how we can approach this are two methods.
okay,
We have to take small elements
okay,
and then integrate them. So how we can take the elements are, either we can take them like this, that is
okay,
in series. This element and this element are in series.
yes,
So we find out the capacitance of combination of these three in series,
okay,
and using a general formula that we obtain from this combination,
yes,
we apply the parallel formula to obtain the entire capacitance.
okay.
Or we can take an element like this
Okay.
and then take different series of this element. So we
Yes.
have to decide which element would give us the simpler, would simply give us the solution.
Okay, so what you are saying is that we can find the effective capacitance, like, but for that we have to do in a parallel or series combination. And if even if you are doing the parallel and series combination, there are three parts. There are three
Exactly.
subparts. Okay.
Exactly.
Okay.
So the formula for series is effective capacitance is 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3.
Yes.
Whereas for parallel it is C is equal to C1 plus C2 plus C3.
Yes.
So we see that this formula looks much more simpler,
Yes.
and if we take this element of say width dx,
Okay.
so we will see that area of the non slab part
Okay.
is constant
Yes.
throughout all different
Hmm.
sections.
Okay.
It is equal to let us first calculate, this is T.
Okay.
So for the slab we will find that this is equal to T secant theta
Yes, that length can be easily found at
from
this-
using trigonometry.
Okay. T sec theta.
So if this is A,
Yes.
so the area corresponding to the non slab part
Okay.
would be equal to A into A minus T secant theta. This is the area of the small element
Okay.
slabs corresponding to non slab part, non
Total area that is corresponding to non-slab part.
total area, adding this
This
part
one
and this part.
Okay.
So if we write, and we can add those, since they are in parallel, we can simply add the capacitance. See, capacitance is given by epsilon naught A by the D. So here D is actually
dx.
a small element,
So let's figure this.
and A is equal to, as we have already written here,
Yes, total area.
so which gives us epsilon naught A into A minus T secant theta
Upon
by
dx.
dx.
Okay.
Now the capacitance of the slab part, the area corresponding to it will be equal to epsilon, just epsilon,
Okay.
or we can write
Epsilon naught k also.
epsilon naught k.
Yes.
Exactly, epsilon naught k
Hmm.
into area. Area would be A into T
T sec
secant theta
Yes.
by dx.
Okay.
So a parallel combination of these two should give us the net capacitance of our small.
of this dx part.
That would be, since dx is common,
Yes.
and we'll get it as 1 by dx. We can take epsilon naught common as well.
Okay.
Epsilon naught A K T secant theta plus A minus
T sec theta.
T secant theta.
Okay.
So this is the capacitance of
dx part.
the element that we have taken like this.
Yes.
Now we have to add all such elements to find the total capacitance.
Okay. And these elements are in series. Yes, series.
Exactly.
Okay.
So the series summation would be, integration of 1 by c of all small parts, say dc, it would be equal to integration of dx by epsilon naught a k minus 1 plus a. So if basically we have to integrate dx, that would give us the width d, and from trigonometry we can find that d is equal to a cot theta.
Yes, d is equal to a cot theta.
How to find that? See, this, consider this triangle, this side is a, this theta, this angle is 90 minus theta, so you can find this as a
Cosec theta.
A cosecant theta. So once this is a cosecant theta, now consider this triangle, and since this is the angle theta, this a cosecant theta cos theta, that is a cot theta.
Okay.
So this gives us 1 by c is equal to a cot theta by epsilon naught a cancel, t secant theta k minus 1 plus a.
Okay. By this we can simply find the capacitance of the system.
It would have been much difficult if we would have taken an element like this.
Yes. Okay. Yes, so it shows like in some kind of difficult problems we can take elements and then integrate. So
Yeah, choosing the element becomes very important in such cases.
yes. Okay, so let's move to the next question. Three conducting shells are placed concentrically. The middle shell is grounded. The inner and outer shells are given charges Q and minus Q respectively. Find charges appearing on surfaces of shells A, B and C. Use the diagram that is given in the question. So Shrikant will tell you how to approach the question.
So let us establish few basic things. Since the middle shell is grounded, the potential of middle shell, say VB, is equal to 0.
Yes.
That is very obvious.
Yes.
And we know that the net charge on this shell, A shell, is equal to Q, and net charge on C shell is equal to
Minus Q.
So let us draw another diagram. See, the charge contained on the inner side of the A shell will be 0.
Okay.
Can you explain why?
Inner side. Because it is a conducting, so charge always remains on the surface of the.
Yeah, if you draw a Gaussian surface,
Okay.
this,
Okay.
since E within the metal is 0,
Yes.
so flux would be 0. That means Q enclosed inside has to be 0.
Okay.
So this is 0, and outside it will be Q.
Okay.
The next shell, if this is Q, using the similar principle,
Yes.
inside the charge should be minus Q.
Yes.
And since it is grounded,
Yes.
cannot apply law of conservation of charge. It is not isolated.
Okay, because the charge, Earth has infinite charge. It can always supply to it according to the situation that the potential becomes 0.
Whatever the situation demands.
Yes.
The situation here is VB has to be 0.
Okay.
So it will supply enough charge to maintain that situation.
Okay.
So let us assume arbitrary charge Q on the outer surface.
Okay.
If there is a arbitrary charge Q on the outer surface of B, then there has to be minus Q charge on the inner surface of C.
C. Yes.
The same principle.
Yes.
And outside, since its total net charge is minus Q, it has to be Q minus
Small q.
Small q.
Okay.
So this is what we have established till now. Now let us write the condition for VB is equal to 0.
Okay.
The potential at this shell.
Yes.
So let us write, because of inner shell it will be Q by B, KQ by B.
Because of the charge of shell A.
We can assume it to be present at the center.
Yes.
Next, because of this minus Q charge, it will be K minus Q by B.
Okay.
Because of this Q charge, it will be K Q by B.
Okay.
Because of this minus Q charge, it will be
K to minus Q upon C, and for the last one it will be K into Q minus Q upon C.
exactly. So we'll see that these terms cancelled out.
Yes.
This and this cancels out,
Okay.
and remember this is equal to 0.
Okay.
So which leaves us with KQ by B is equal to KQ by C.
Yes.
Exactly. So K can be cancelled out. So Q is equal to B into Q by C.
Yes. So we have found the capital value of capital Q in the terms of small q.
So using this we can find charges induced on
All surfaces.
all surfaces. That solves the
That
problem.
was our aim. So by using the simple thing that if we get a Gaussian surface on the inside of a metal, because the flux is 0, so electric field is 0, so the charge enclosed must be equal to 0.
Use
So-
that principle to find out the charges on particular surfaces.
Yes. So because of by using that principle, we obtain the charges on different surfaces, and we solve this question.
Exactly. There can be modifications to these type of questions. There can be things like, say, these two shells have been attached using a wire. So simply you have to write down those particular conditions, and you'll get the value of unknowns. Say if these are attached with a wire, then simply what will happen is both of these potential of both of these will be equal to 0. So it's a simple thing. Try out such questions like that.
Okay.